Hello everyone, I'm Wang from the Intuitive Computing Lab at Johns Hopkins University. Today I will talk about a new way to demonstrate tasks and actions to robots. As a growing number of people have robots in their homes, my goal is to enable everyday users to customize robotic assistance based on their individual preferences. One way to achieve that goal is robot programming by demonstration, which enables a robot to learn new skills by imitating a human expert. This field has been an active research area for years. There are several survey papers and various authoring methods that has been proposed relating to this project. One of the authoring methods is kinesthetic teaching, where a user physically moves a robot to demonstrate a new skill. Kinesthetic teaching doesn't require external sensors and can simplify motion planning for robots. However, kinesthetic teaching can be hard to accomplish when using high degree of freedom robots, such as robotic hands. Compared to kinesthetic teaching, vision-based demonstration can be a more intuitive approach, because it is more similar to how a human teacher teaches a human student. Most works on vision-based demonstration use third-person videos as input. However, a common limitation found in third-person videos is the problem of occlusion. For example, this video shows a human teacher demonstrating how to assemble a chair, and was taken from a third-person viewpoint. From this point of view, it would be difficult for a robot learner to see how the human teacher inserted the screw into the parts. In this way, occlusion may prevent learners from effectively learning skills by limiting the visibility of the teacher and the understanding of the learner. Because of the occlusion, the teacher has to consider and estimate learners' perspective during the demonstration, which increases their cognitive load. At the same time, first-person vision enables a learner to directly channel a teacher's perspective. This perspective can clearly show hand movement, especially showcasing hand-object interaction. Moreover, first-person vision also captures users' attention and can provide insight about his or her intention. Last but not least, first-person vision reduces the need for fixed external sensors, so it is especially useful in real-life applications. Due to these advantages, the computer vision community has been studying first-person vision for years. However, there is relatively less work on first-person vision in human-robot interaction, especially in robot programming by demonstration. Let us revisit the same assembly task shown earlier. When a girl is assembling the chair, what does it look like from the first-person viewpoint? She first connected two parts, and then inserted a screw. Now we can clearly see how she inserted the screw. Then she flipped the chair and screwed the pieces together. In the first-person video, we noticed a dynamic viewpoint change. When the demonstrator was connecting two pieces, the chair was in this viewpoint. Then, the demonstrator flipped the chair to another viewpoint for screwing. The first-person viewpoints match how people naturally perform manipulation tasks and captures users' preferences. To leverage the first-person viewpoints, we developed a hierarchical structure to synchronize 3 degrees of information in a complex manipulation task, including sequential procedure, spatial configurations, and first-person viewpoints. This information can be used to program a robot. We call this programming by first-person demonstration. The programming workflow includes 2 stages. In the first stage, viewpoint information was collected from human demonstration. Later, the first-person viewpoints are leveraged by a robot to provide user-centric robotic assistance, in which the robot presents parts to human matching the first-person viewpoints. Now, let's watch how people perform the same task with and without user-centric assistance. When the robot provides user-centric assistance, in other words, the robot presents parts following the first-person viewpoints. The participants finish the scoring task naturally and smoothly using her right hand, which is her dominant hand. Comparing this with the case where the robot doesn't provide user-centric assistance. Here, the robot presents parts matching the static viewpoint on the cover page of the IKEA assembly manual. As you can see, the user had to tilt her head to find a better viewpoint to insert a screw. And finally, she screwed 2 parts together using her left hand, her non-dominant hand. These examples highlight the potential of first-person vision to foster a smoother, a more intuitive collaboration. Next, I will talk about the user study we conducted to explore how the user-centric robotic assistance may shape users' behaviors and experiences. There were 2 conditions in the study. As mentioned before, in the standard assistant, the robot presents parts matching the viewpoint on the IKEA assembly manual. On the other hand, the second condition, user-centric assistance, used first-person viewpoints collected from a head-mounted camera. The study used a within-participant design, and the order of conditions was counterbalanced. We recruited 20 participants for the user study. Due to time constraints, I will only highlight part of our measures and results here. For the complete measures and results, please refer to our paper. A primary goal of our study was to determine how the type of robot assistance may influence participants' behaviors. So we employed 2 behavioral measures. One measure was the number of times the participants dropped the task tool, the screwdriver. The other measure we employed was the number of times participants switched between hands or used their non-dominant hand to finish the screwing action. Moving to the results, we found that less unproductive behavior was observed in the user-centric condition. Both tool drops and unproductive hand use were less likely to occur. This implies the user-centric assistance may have the potential to minimize disruptions within human-robot collaboration. With regard to our subjective measures, the participants perceive the user-centric robot to be a more considerate collaborator. By presenting objects matching the first-person viewpoints, the user-centric robot avoided unnatural object pose, and thus was perceived as a better collaborator. In the post-experiment interview, one participant said the user-centric robot could feel when he was uncomfortable. He felt he and the robot were working together. In summary, this work explores how first-person demonstrations can be used to enable user-centric robotic assistance. We believe that capturing users' preferences via first-person demonstration can aid robots in providing natural assistance. Other advantages of first-person vision, for example, the portability of first-person cameras, may accelerate the development of robot programming by demonstration. Thank you for listening. Should you have any questions or comments, please do not hesitate to email us.